Hey everyone, the purpose of this video is to look at the effect of the sensor filtering on feedback control. The content of this lecture is going to come from Chapter 8 of Chemical and Bioprocess Control, the 4th edition by James Riggs. Alright, so this slide shows what a noisy sensor looks like. All sensors are going to have some degree of noise, and what noise is it's going to be a measure of variability around the actual value that the sensor is measuring. So the sensor value can output a value that's plus or minus the actual value based on the variability associated with that particular device. And so variation can occur that's not real variation of the process. If this variation isn't filtered or accounted for, this variation in the sensor noise can cause the manipulative variable to change unnecessarily and disturb a process. The figure below here, if we look at the top curves, which show the product temperature, the thin line in this plot shows the sensor reading, which is a noisy sensor. So you can see there's quite a bit of variation in the output of the sensor. If this signal is filtered or a running average is taken, the dark line is shown here. So this dark line is a better measure of the true value that's coming out of the sensors, or a better measure, more representative of the actual process. Okay, so if the sensor is not filtered, the manipulative variable can change in response to the noise. So the way the way feedback control works is the set point is going to be compared against the sensor value, and if the sensor value has a lot of noise associated with it, the error that goes into the calculation by the controller is also going to have a lot of noise. And that's going to cause the controller to tell the manipulative variable to increase or decrease in response to the noise when the actual process itself is not disrupted. Okay, on this plot we can see what the effect of filtering is on the process. So if we look at the top plot, again the product temperature, this dark curve on here shows the actual measure of the CV, the control variable, with the noise taken out of it. So this is the response of the product temperature to a step change in the set point. The thin line on here shows the filtered value of the sensor. What you can see is that the filtered value of the sensor is going to respond slower, so there's going to be a little bit of a lag associated with filtering the sensor. And this is going to make sense because we're averaging many values that's coming out of the sensor, and we can only average values in the past, so it's going to cause a little bit of a lag to occur. We can also see, because of the average, there's going to be less variability in the filtered value relative to the actual value of the process. But the benefit of this is that the manipulative variable is going to change in much smaller ways. So we can see on the plot, on the figure below here, the manipulative variable in response to the step change, we have the initial drop and only slight variations in the manipulative variable. So we don't have the noise that we saw on the previous slide for a noisy sensor. Okay, so let's review and just look at what the block diagram is for a typical feedback control loop, which is shown here. So in this process, we have a set point that's a user entered value. So this set point is going to be compared to the value coming out of the sensor to give us an error. This error the controller is going to use this error to calculate a change in the actuator input, such as like air pressure, valve position, etc. The actuator is going to change the input to a process, which could be a flow, for example. Then the process is going to be affected, so the output of the process, which is the control variable y, is going to then be sent to the sensor. And the sensor is going to measure this, and the output is going to be the sense value. We can also have over here disturbances that affect the process as well. Okay, because the sensor value can be noisy, and typically what we should say is that the filter is added after, so a filter function is added after the sensor. Typically in practice, a sensor is going to come with a filter feature on it, which you can enter in a filter factor, which is a specific value that allows for filtering of the sensor signal. All right, so this filter value is the sensor value is going to be filtered, and this filter value is now going to be compared to the set point to calculate the error that's used by the control algorithm to change the process. Now, something that's important to remember is that the characteristic equation, right? So our characteristic equation, if we remember, this characteristic equation is the denominator of the transfer function of the closed loop process, right? And so this is going to be 1 plus the product of the transfer functions in the loop. Okay, so now in this case we have 1 plus the product of the transfer function in the loop is GC, GA, GP, GS. This is what it was previously, but now we're going to have a transfer function for the filter. So we need to know what this transfer function is. In practice, really what you need to know in terms of applying a filter is this filter feature is we're going to have this filter value f, and this filter value f is going to be a value we add to the sensor to give us a smooth signal. If we want to do things like assess the stability or see how this filter factor affects the dynamic response, which is one of the things we like to do in theory, sort of in practice, this is something that you can figure out by tinkering a little bit. But again, this is something that we can use the characteristic equation to see how filtering affects both the response and the dynamic behavior, so how much oscillations, the speed of response, etc. So we're going to do that here. All right, so we need to first know what the transfer function is for the filter. And so typically filters use a first order process. So we're going to have a first order filter, and this is pretty common. And so a first order filter, the differential equation for a first order filter is tau f, so the time constant, times dyf, this is our filter function dt, plus the function itself. So it's the time constant times the derivative of the function plus the function equals, it's typically going to be the gain multiplied by the input function, which is going to be ys. So in this case, for a filter, we have a gain that is going to be equal to 1, so we don't need to worry about the gain here. Because remember, for a filter, we want the filter value to change by as much as the sensor value changes. If the sense value changes by 80 degrees, we hope the value coming out of the filter is also going to change by 80 degrees, or that's a problem. All right, so again, if this is our differential equation, if we do our Laplace deviation variable, derive our transfer function as we've done previously, we can determine that the transfer function for this first order process, like all other first order processes, is going to be the gain divided by time constant times s plus 1. All right, so this is something that we would need to use to assess the stability, or use this within the characteristic equation. Filters on centers are going to use a value called a filter factor. Okay, so we're not going to go into detail on some of this math, but I'm going to show you a little bit about what the filter, I'm going to give you a little bit about how the filter factor is defined. So the filter factor, it's defined as f equals 1 over tau f over delta t plus 1. Or we also are going to need to use this later. We can rearrange and we can solve for tau f in terms of f, and this is going to be delta t over 1 over f minus 1. Okay, so tau f, this is what we know. This is the time constant. F, this is the filter factor, so this is going to be the value that we can actually enter into the sensor to filter the sensor reading. And this delta t is going to be the time interval over which the calculations are made. So typically in like a distributed control system, feedback control is calculated every few seconds. So this would be the amount of time, the time interval through which the calculations are occurred. All right, so we're gonna look at how this is applied in terms of coming out of the sensor. So I need to give you a few equations first so that we can look at how this is used, and then we'll look at how filtering affects the dynamic behavior of the process. Okay, so the way that we filter a process measurement is, we have a value, so yf of t. So this is going to be the filtered value coming out of the sensor. So the filtered value coming out of the sensor is going to be equal to f times y it's going to be f times ys of t plus 1 minus f times ys of t minus delta t. Okay, so this is how we want the filter to work. So this is how things are going to be implemented in practice. So the filter value is going to be this filter factor f multiplied by this value right here. This is going to be the current value, the current value coming out of the sensor. So we have the value that's coming out right now. And then it's going to be added to 1 minus f times the previous value. So this previous value would be stored in the DCS, the controller, and it would be used to calculate or stored in the sensor to calculate the filtered value coming off. Note that this previous value is going to be a filtered value of the previous value plus the one before that. So you can see how this keeps a running average of multiple readings. Now this f can range between 0 and 1. Actually, it can't quite be 0 because a 0 filter would take none of the current readings, so it has to be at least 0.01 or something very small. But if we wanted no filter, that would mean f equals 1. So f equals 1 means the filter value is all of the current value, none of the previous value. So there's no averaging of previous measurements in here. Okay, so this filtering is going to reduce the effect of the sensor noise by approximating a running average. But the consequence of this is because it's a first order process, it's going to add a lag. So filtering is going to add lag, but it's going to reduce the variability caused by the noise. Because it adds lag, we want to use the minimum amount of filtering necessary for the process. Okay, so again, this filter value can be a value between 0 and 1. So the smaller the value of f, so the closer f is to 0, say for example 0.1, the more filtering there is going to be, which is going to be more lag to the process. Okay, so to see the effect of the filtering on the dynamic behavior of the closed loop process, we're going to do a little exercise where we're going to look at the characteristic equation. Okay, and for this we're going to use a p-only controller and we're going to use a first order process. So there are some other things in here like actuators. So we're going to assume a fast actuator. That would mean the transfer function is 1. We're going to assume a fast sensor. So the transfer function for the sensor is 1, but the sensor is noisy, so we're going to filter out the sensor using the first order filter. We can't have a fast filter. The filter is going to work the way that it does, and it's first order by nature of the filtering because we're taking that running average. All right, so here's our characteristic equation where we have the transfer function. We have the transfer function for the controller, we have the transfer function for the process, and here we have the transfer function of the filter. Okay, the actuator and the sensor equal to 1, so these transfer functions plus 1 equals 0. We can do, in order to determine the time constant for this process, we have to rearrange this equation and put it in standard form. We've done those things before, and then calculate a new, so this right here is our time constant with filtering. So we can see the time constant with filtering because this tau p is going to be because this tau p is, or tau f is going to be less than 1, this time constant is probably going to be smaller, but also we have to consider what the values of these terms are as well. In general, we can't really get a lot of information about the time constant, but what we can see is we can get some information in terms of the damping factor. So the damping factor is going to be a measure of how fast the process dampings up. Notice here that we have the product of the taus in the numerator or the sum of the taus in the numerator and the product of the taus in the denominator. So how the filtering affects the damping factor is going to depend on the relative value of the filter, the relative value of the tau of the filter to that of the process. All right, so something that you can do on your own is you can check this, what I'm going to discuss on the next slide. And the way that you can verify this and see that it's correct is pick two cases. In the first case, pick tau p equals 10 and tau f equals 0.1. And in the second case, pick tau p equals 0.1 and pick tau f equals 10. If you do this, you'll see the analysis that I discuss on the next slide holds true. I'm just not going to go through this math, but this is something that you should do because you will probably see something on this a little bit later. Okay, so first, remember that what we showed on a previous slide is that tau f is equal to delta t times 1 over f minus 1. So as f becomes small, we have more filtering, and this value is going to become large. So tau, this value is going to become large as f becomes small. So for a given time constant on the process, we can change tau f between a small value and a large value. So how much filtering is going to change what happens to the process as we change the amount of filtering. Okay, and so this is maybe a hard thing to grasp, which is why I told you on the previous slide to check those cases and see what happens. Okay, so if tau f is small compared to tau p, okay, the damping factor zeta will decrease when tau f is increased. So again, how do we increase? So tau f is increased when f is decreased. Okay, so if we make f smaller, right, this smaller, this makes tau f bigger. So a smaller value of f causes more filtering. Okay, so on the contrary, when tau f is large compared to tau p, the zeta now is going to increase when tau f is increased. And again, so as we decrease f. So again, depending on the relative value and where we are and how much filtering is occurring, if we increase or decrease the amount of filtering, we can see a differing effect occur on the damping factor for the process. Okay, so again, this is a little bit of theory about how things change in response to adding filtering to the process. One of the things that you can do is, again, you want to be careful and you want to use the minimum amount of filtering. So start with a filter value close to 1, and then slowly add filtering to the process to get the response that you need. And again, some of the things you can look at is really the variation in the manipulated variable in response to what you expect your process not changing. So here's some examples of how the process can look. This is the effect of filtering on an open loop response. So here we have filter temperature as a function of time, and it looks like there was a step change that was made to the input to the process. So for a very small, so this right here is lots of filtering. Over here, this is less filtering. What we can see is with less filtering, that the response has a little bit more noise. As we add more filtering, we see the effect is less noise, so less variability in the filtered temperature, but we also see more lag. So again, initially we have this lag right here, and again, as we add more filtering, we see that the process is going to respond slower due to the lag added by the filter. So again, we want to add enough filtering so that we don't have too much variability, but we don't want too much filtering such that we add a significant amount of lag to our process response. Now, it's important to note that you can actually have too much filtering. So again, looking at these curves here, so now here we have a small amount of filtering, so we're using about half the current value. So we can see the curve right here, this curve right here is really noisy. And as we decrease the amount of filtering, what we can see this dark curve, right? We get more oscillations, so we see an increase in the damping factor for this case. But there's also less noise, and then as we again increase, so this right here is a lot of filtering. So we're only taking 1% of the current sensor reading. And what happens there is we can see that we have a significant amount of lag relative to the initial process, and we also have a more damp process. But one of the things that you can see is that in addition to having this more lag and this less variation from the actual set point, you can see that with too much filtering, we can actually cause extended oscillations on the process because we're filtering all of these values still. So this value over here is still considering some of these values back here. So in this case right here, there would be way too much filtering on the process. All right, looking at the effect of the filter factor now, so this is more related to the topic that we looked at. Here's an example. Here's a figure that shows actual data. Okay, so we can see here, this is a sensor value where the control variable is not changing, but yet the value that we look at is changing by a little bit. We can see this blue curve shows the noise. If I use Excel and I take a 5-point average, I get the red curve in here. So the red curve, we still see a little bit of noise associated with it. If I take, again, the green curve on here shows the 9-point average. And again, we can look at the filter value as well. So on this next plot, okay, so again, no average, red is the 5-point average, green is a 9-point average. You can see that there's always going to be a little bit of variability, but again, we're kind of zoomed in a little bit on this value, so we would expect something as we zoom in more. Okay, if we look at this plot, and I'm going to move this over, a filter value that's close to 1, right? So the green looks exactly like the blue. As I change this to 0.9, we can start seeing that we're starting to decrease the variability, 0.5, right? So we have a little bit of filtering. So this is looking maybe closer to like a 5-point average, or this is really like a 2-point average. If I go to a 0.2, this should look a little bit like the 5-point average. The 9-point average would be about 0.1. Okay, so now it looks like that. And as I continue to filter, now what you start seeing is that we start seeing this lag show up in the beginning. So we have this lag followed by this running average. So that's how the filtering works. It essentially takes a running average, like you take an average when you use Excel. Okay, so we're going to stop there, and we'll see you next time.